Hi, so thank you for waking up and getting up the hill this morning again. So today I will continue with essentially cosmological probes of, at the end of the day, the mechanism that I have been discussing. And as I said yesterday, and I would like to emphasize that they are only examples. Any kind of bees that would give rise to same kind of signatures could be tested in the same way, but you have to redo the full analysis to really put constraint on your theory. I have put my lecture notes of the two last lecture online. Again, if you have questions, I mean, there are much more details in the lecture notes than what I could do on the Blackboard. So if you have questions, if you find typos, if you have comments, everything is welcome. Don't hesitate. Now, about this lecture of today, as I said yesterday, my personal bias, essentially, is to talk to you about two kinds of probes, early universe CMB1, okay, and late universe 21 centimeter cosmology and Lyman alpha forest. As I said yesterday, CMB is a fantastic probe of cosmology, among other things because it is, you can work with it in linear theory, so there is no astrophysics uncertainties. It's not completely true, but obviously it's much more clean than the other probes that I will discuss. So let me begin with that, with CMB and recombination. So at redshift much larger than 1000, the universe is fully ionized, and you have a tightly coupled plasma of baryons and photons. Around redshift 1000, you have recombination. Electron and protons recombine, and essentially your photons are going to be able to stream up until today. I mean, this is essentially if it was instantaneous. The whole story of the ionized fraction, very roughly, I will refer to ionized fraction as Xe, which is the number of free electrons divided by the number of baryons. As a function of the redshift, two important redshift would be the redshift of recombination, so around 1000, and redshift of reionization, around 10, order of magnitude. So, universe fully ionized originally, around recombination, it goes down. Again, in order to know how these things go, you have to solve Boltzmann equation. I will just briefly discuss them for the ionized fraction. At the end of the day, you can check. This is supposed to be 1, I'm sorry, but okay, let's go like this. This is log scale, this is 10 to the minus 4, okay? You can see that you can check, just looking at your lambda SIMDM, solving the evolution equation for your ionized fraction in the early universe, that in standard model cosmology, it could go approximately to 10 to the minus 4 and slowly go down, up to the moment where actually we have stars that are going to produce a UV background that is going to begin to reionize your universe. This should be very well modeled through photoionization processes, photo heating, and so on. In most of the CMB analysis that you will find, this is really modelized through a tangent hyperbolic, okay? So all the constraints you get from Planck data, for example, are usually done assuming that you have just a tangent hyperbolic thing that goes up back to 1, okay? Reionization. For this part, you have very nice tools in order to compute the evolution of a Boltzmann equation with much details. If you have ever heard about them, it's RecFast, HiRec, that are actually directly used in Boltzmann solver to look at the evolution of perturbations in all your fluids, like class and camb. Before getting to the fluctuation, we have the beautiful cosmic microwave background black body spectrum. So if you look at intensity as a function of frequency, you have what should look like a black body spectrum, okay, with a peak around 160 gigahertz. And this has been extremely well measured, so I'm not going to try to like draw error bars because we wouldn't be able to put them on this plot for most of this part, okay, above gigahertz frequencies. So this has been very well measured around all the thing here around the peak by Firas-Kobe. Now, and from the peak, you can extract the temperature of the CMB, which is 2.75 Kelvin. Now, as I briefly mentioned, we have some fluctuation on this, okay, at the order of 10 to the minus 5, okay. And most of the physics information, among other things, what is the content of a universe in terms of baryons and dark matter, we get them from studying these perturbations, in particular, two-point correlation function of these fluctuations. So what I would like to do if I had many hours, I would look at how to get to the two-point correlation function of temperature perturbation in the photon spectrum, okay? And by Fourier transform over a two-dimensional sky, okay? So I don't have the exponentials of E minus exponential minus EKX. But I have to essentially develop in terms of multiples, so angle in the sky is going to be the dual of the multiple, essentially. It goes inverse compared to each other. And I would get what is usually referred to as CLs, temperature fluctuation squared. That I'm going to try to make something a little bit nicer than the other days. Hops that essentially go like this, micro Kelvin square as a function of L. So large L, small angles, big L's, small L's, big angles. Here you have large uncertainties. For the rest, this is extremely well measured, among other things by Planck data. But before even that, we had also WMAP data and so on. As I said, the very nice part of this is that it's linear perturbation theory. Huh? So at the first lecture, I was also asked, the first answering question I was re-asked what are the hints we have about dark matter from the CMB. The first thing that was essentially that to have perturbations in the sky of the order of 10 to the minus 5, actually, assuming that you have originally your baryons and your photons that are coupled, right? You have to start from that before being able to really grow in terms of perturbation. Perturbation in matter fluid goes as the scale factor between 10 to the minus 3, and today you have only 3 orders of magnitude compared to 5. You have no time if you have just baryons who go to nonlinear structures. Obviously, there are much more than that. From there, I would not give you exactly what is the value of the amount of baryons and photons that baryons and dark matter that we could have. So another hint of how you can get this information is by looking at these quantities. So a certain distance in L corresponds to a certain angle in the sky. Okay, so I will refer to this as sound horizon angle. And so if I have to put, this is about 100, and this is about, where is it? 1,500 here, just to have orders of magnitude. And this is what I will call the damping angle. So my spectrum is not flat here, it goes down, okay? It's damped. the distance between the peaks here is completely driven by sound horizon. The sound horizon that essentially depend on uh, uh, the sound speed in the plasma at the time where CMB was released, essentially. And this strongly depends on the amount, on the relative importance of baryons compared to photons, okay? So from measuring this distance, which is of order of 100, okay, in L, between the peaks, you actually have an information. So if I look at an angle, okay, I can relate an angle to a distance in the sky. Let me call it y instead of r for the moment. This is, I'm here, okay? I look at the distance in the sky, corresponds to an angle, and this is angular distance, okay, from basics. I can essentially say that I mean, it's far away, right? Okay. So my angle in the sky should be of the order of y divided by the angular distance. I would like to go to co-moving quantities, okay? So I have scale factors in y and in the scale factor, in the angular distance, sorry. So this would be the co-moving distance y divided by the co-moving distance to the CMB, essentially, to last scattering. This distance between essentially, typically, two peaks, this L of 100 corresponds actually to, you can compute the sound speed horizon, so which would be my moving quantity here, yc, okay, from 0 to a certain time, conformal time, okay, that depend on the sound speed on the plasma, okay. This quantity, this sound speed, at the time of last scattering, okay, is actually 145 megaparsec. In standard model cosmology, and the moving distance to last scattering is actually of the order of 14 gigaparsec. You make the computation, I mean, thinking of theta as 1 over L, okay? And you will essentially see that at the end of the day, this theta corresponding to sound speed versus distance to last scattering is essentially order 100, which is what you see in this plot that you have measured, okay, with very small error bars. This is completely dependent on the sound speed, that completely depend on the relative ratio of baryons to photons, okay? This is one way to have information on the amount of baryons. If you know the amount of baryons, you know that you are missing something, right? This is already something. And I mean, in order to compute this, I had to essentially also introduce the time to last scattering, and in order to compute this time, I have to assume something about what is inside my universe. I have to assume that I have baryons, and again, it won't be working if I don't put something else, which is dark matter, okay? So this quantity directly depend, I mean, just without doing the full analysis, this quantity depends both on the amount of baryons and the amount of dark matter that you have, cold dark matter. Things, by cold dark matter, I just mean something that doesn't have strong interaction with photon, which is not part of this baryon photon plasma in the early universe. Another interesting scale, it's this theta d. So this was for theta s. For theta d, the diffusion scale, the scale from which your power spectrum is going to be damped strongly, you can directly relate it to the mean free path of photons into this plasma right after last scattering. And this quantity depends on, actually, again, the number density of free electrons at that time, and the Thomson scattering. So this is another, so lambda d. The diffusion scale is lambda d square is actually related to this mean 3 path. Again, you can relate lambda d, okay, to a certain value of L. If you plug the numbers I gave you at the beginning of the school, you compute this explicitly, again, assuming that your universe has a certain content, you are going to get to theta d's of the order of 1,400, which is also what you see on the plot, okay? So without doing the full analysis, okay, these are hints of how we can extract the information from cosmic microwave background, okay, two-point correlation function on what is in the what is in our universe, in particular, the baryons that are responsible for this. And maybe I don't know if I mentioned that. I mean, one way to understand baryonic acoustic oscillation is just that in the plasma, just before being released, essentially you had photons that gives you pressure, but that are coupled to baryons that gives you gravity. Okay, so at the end of the day, you have something that does like that. I mean, okay, oscillating plasma, which gives you the wiggles. Okay, and obviously you can, I mean, relate the wiggles, the distance between the wiggles, to the content in baryons and photon. Okay, good. Let me repeat that CMB is not the only probe we have about the amount of baryons we have in the universe. We have Big Bang nucleosynthesis, which is another very strong probe, and they agree with each other, okay? So that's a good point. Good. So now I said that I have the ionized fraction here, and I would like essentially to estimate the ionized fraction, how the evolution of the ionized fraction around recombination, okay? I need Boltzmann equation in order to essentially look how these processes are going to go out of equilibrium. Electron, proton going to hydrogen photons. In order to do this, I essentially have exactly, you will recognize UV operator, okay, on electron number density, and on the other side, I must have equilibrium density of my the electron and protons times the annihilation cross section that is here. I mean, for this process, okay. And then I should have, on the one hand, hydrogen and photon. Now, it happens that photons, the number of photons in processes is essentially not conserved. Think of electron positrons going to 2 photons. I can have Bremsstrahlung from photons, from electrons from the first part of the initial part, and I have, with the same initial state, electron positrons, I have 3 photons, okay? So this means that essentially, I have to set the photon chemical potential to 0, essentially, meaning that number of photon divided by number of photon at equilibrium is just simply 1. Okay, this is why they don't appear in this equation. And then I have number of electron, number of proton, number of electron equilibrium. Sorry, number of proton at equilibrium. So this is from the same, exactly same reason that I did dark matter. This is my evolution equation of my number density of electrons in, at the time of recombination. These are the processes that are in the game. My whole goal is to go from here to ionized fraction, which is NE over NB, okay? Details are in the notes. I won't go through this. But at the end of the day, I get an equation for the ionized fraction as a function of time that have two parts. One part that is ionization rate, and the other part that is recombination rate. Both of them depend on this cross-section, okay? But I mean, this is what I have to compute. You can actually, I mean, do this in a relatively simple way, assuming a simple expression, I mean, a simple model for hydrogen. You can go to further detail, which has been done. I mean, in these codes I mentioned, high rec, rec fast, and so on. And you can really look at the evolution of this ionized fraction and get this curve I was showing before, okay? Point is that my dark matter story is going to change this part of the equation when I will look at energy injection, okay? So this is, I just put it, I just tell you where it comes from and where I'm going to change the story as soon as I will put dark matter in the story. Now, once I have the ionized fraction, I can compute my optical depth, okay? Or my mean free path related to my mean free path of photon around that time. Optical, this is sometimes going to be the decay lifetime of my dark matter, and sometimes it will be optical death. So please listen when I'm discussing, because I might forget to put tau dark matter when I'm talking about decaying dark matter, but okay. So this depends on the amount of electrons I have in the story and the Thomson cross-section. You can actually realize that the probability that a photon last scattered into a certain piece of conformal time, okay, is directly related to the conformal derivative of e to the minus tau, okay, between e to the minus tau, which at the end of the day is the transmission probability of photon. This quantity is called the visibility function. And you can draw this visibility function, again, assuming a certain universe, a certain content, and a certain number of things that are entering into this equation, okay? Standard model cosmology, you will get J eta as a function of conformal time. If I zoom around redshift 1000, I will get something that goes like this, okay? So, oh, I should maybe give you the width approximatively. So what this tells you is that last scattering is not one moment at 1100, okay? Last scattering is actually a last scattering surface. It's not last scattering time, okay? And again, as soon as I will put dark matter energy injection, I will modify this, I will modify that, and I will modify that. The larger is my light scattering surface, the more is going to be my signal blurred, essentially, okay? The more I'm going to affect my peaks here in the CMB. Very good. So without going to the details of linear theory perturbation, this is all I will tell you about cosmic microwave background that I will use, okay? Now, maybe I keep this and I erase that. Second probe I want to discuss, 21 centimeter cosmology. Why? Because it's the next one in the story of the universe. Remember, I draw you a line of time yesterday, redshift 1000, recombination between redshift 20 and redshift, say, order 10, you expect to have in the near future 21 centimeter cosmology probe of the history of the universe, and between redshift 6 and today you have galaxy surveys and other things. You will have actually Lyman alpha forest observation, which is the last one I will tell you about, okay? Because I have CMB, 21 centimeter, and then around this time I will have Lyman alpha forest. Okay, what is this 21 centimeter signal? So this 21 centimeter signal arises from neutral hydrogen, which we expect to be ubiquitous in the universe in this period. So it comes from spin flip transitions between the two ground state energy of neutral hydrogen. So essentially, you have two possible orientations of proton-electron spins, opposite or parallel, and this gives a small splitting between the two ground state energy levels of neutral hydrogen, okay, that give rise to photon of frequency in the rest frame of a size of 21 centimeter. This corresponds to a frequency, let me write lambda 21, nu 21, which is 1020 megahertz, okay? Very good. So imagine you have, say, photons of this type that are emitted in some clouds of neutral hydrogen somewhere around redshift 20, okay? Then they rise to us. Essentially, they are going to be redshifted, okay? They are going to be redshifted, order of magnitude, say 10 by 10. So you get to hundreds of megahertz, okay? Hundreds of megahertz, this can be tested by a radio telescope on Earth. Okay, so this is why we are interested into this signal. The other point is that actually this transition rate between the two ground state energy levels, 0 and 1, ground state. So it's, but we call it, singlet state and triplet state. It's the transition rate is very small, it's very suppressed. It's of the order 10 to the minus 15 second. Now, it's not spontaneous transition rate that is going to do the whole game. You have a bunch of processes that can then induce these kind of transitions, okay? Among the different processes that can induce this kind of transition in the early universe, you have collisions, okay, with other atoms or electrons. You have emission or absorption of radio photons, and the radio photons that we have all over are cosmic microwave background photons, okay? And the last thing is actually to have transitions to the first excited state and go back down. So emission of Lyman alpha photon, okay, through Lyman alpha, through what is called resonant Lyman alpha transitions, actually. You can actually go from originally one state, go up to the first excited state and go down to the other ground state at the end of the day, allowing you to have this transition between the two ground state energy levels. The processes that are relevant in this region of the history of the universe are the two last ones, absorption and emission of CMB photon and Lyman alpha transition, okay? So-called Woutersen field effect, but I'm not sure I'm pronouncing the name correctly. Some more quantities here. The relative occupancy of the singlet state and the triplet state in the ground state depend on the number of degrees of freedom, which are 3 for the triplet state and 1 for the singlet state, exponential of minus the energy corresponding to this transition divided by the so-called spin temperature, okay? Or called excitation temperature. This is a quantity that we are going to want to follow, okay? This is H nu 21, which is of the order of 68 millikelvin. We go back to a problem of counting number of things, okay? What are we going to do? We are going to use Boltzmann equation to look at the evolution of the occupancy of these two energy levels. You can do the full calculation. There is actually a very recent paper few weeks ago, month, 2411, that we do the full analysis just to be ensuring that actually we are actually in an equilibrium state in this period of the history of the universe. We are in a rather equilibrium situation within which the spin temperature is well described as a function of the radio background that I will assume here that is the photon from the CMB, okay? Obviously, you can look at the sources and so on, but this is not what I'm going to look at. Let's assume it's my radio background is photon, and actually the gas temperature. Let me write it like that. And the coefficients here are essentially what they call dimensionless coupling coefficient that depend on the rate of collisions, that depend on the rate of Lyman alpha photon production from stars. I mean, we are at late time here, okay? So this is astrophysics. And CMB photon coupling, okay? As I said, for the time we are interested in, essentially, the collision rate is sufficiently low that we can forget about it. What does this tell you is that at the end of the day, the spin temperature is essentially going to be somewhere in between gas temperature and CMB temperature, okay? What's maybe I should. What do I erase? Yeah, I will do it here. This was CMB visibility function. Let me draw the evolution of temperature in the universe. Maybe I would like to have all the plots one after the other. Okay, so maybe I just erase everything. So let me draw you the evolution of temperature of CMB and gas temperature at redshift below something like 30 up to today. Or no, not to today, okay? Up to reionization, because reionization is a complicated process. Cosmic microwave background is essentially going as 1/8 temperature, okay? So this is, let's say, CMB temperature. Remember that we have computed the Boltzmann evolution equation for temperature of matter, okay? I mean, it was dark matter, but at the end of the day, it was matter. You know that when it is decoupled kinetically from the plasma of photons, it's going to scale as 1/a². Remember that. This is why I did the calculation. So this is why you expect to have a difference between the two, because actually electrons fully decouple from photons from redshift 150 at that level, okay? So there will be smaller. The gas another color. The gas temperature is expected to actually be lower here. Okay? You scale as 1 over a square. Obviously, we don't have just simple cosmology here, because we are at late times. We have stars, okay? These stars can begin to emit at some point X-rays that are going to heat the gas, okay? And this is where essentially I expect the gas temperature to go up, okay? Let's say in my imaginary model of astrophysics, this happens around redshift 50, let's say. Okay? Now I have these equations that tell me that at the end of the day, my spin temperature should be in between the CMB temperature and the gas temperature, depending on what are the processes that are most important. What we typically expect is that at redshifts of the order 30, it's actually the emission absorption of CMB photon that is going to be the most important processes driving the value of the spin temperature, okay? So essentially, spin temperature is going to be, is expected to be of the order of of the CMB temperature early on. So if I draw a spin, I mean, at this point, should be of the order of the CMB temperature around redshift 30. Then, I mean, we have these stars, okay, that begin to emit UV photons, okay? These UV photons include the Lyman alpha photons that are going to be allowing you to do this transition from the ground state to the first state and go back to the ground state to another level to effectively induce spin flip transitions. This is going to slowly couple my spin temperature to the gas temperature, okay? And then it continues to follow the gas temperature as it hits. Bim. No, I have put TK, but it's T-spin. T-spin. Okay, so I would need a model, I mean, to give you the evolution equation of the gas temperature, to put you exactly a scenario of, I mean, a description of how stars goes. Again, there are fantastic codes that do that. I mean, first you should do full simulation. Now, as I said, there are some numerical code that allow you to do that. For example, 21 centimeter fast. Okay, so this is gas temperature. Now, spin temperature and CMB temperature. Now, the point is, what are we interested in? Okay, to measure this 21 centimeter signal. What we want to know, what we want to essentially compute is the relative brightness with our telescope. This is an antenna, okay? Far away, we have some clouds of hydrogen, okay? Certain gas temperature. We have our CMB photons that are going to pass through this gas and that are going to go out of this gas with a certain brightness, okay? The differential brightness temperature, okay, at a certain redshift is going to be depending on the spin temperature, on the photon temperature, and on the optical depth, the 21 centimeter optical depth. It gives you the transition probability through the clouds. Going to the details of this optical depth, okay, you can get that this is going to be of the order of 27 millikelvin times the fraction of neutral hydrogen, no neutral hydrogen, no signal, okay? 1 plus z over 10, 1 minus t gamma over t spin. Okay, there are other factors, but let me stay to the minimal information. I want to be able to draw you this differential brightness temperature on the same axis. Okay. So let's say that This is 0. This was 15. Let's say that this is redshift 6, okay? Let's say. And let's say that reionization is happening there. This goes up very high. I would like to say that typically, just order of magnitude, this would be order, yeah, 10 Kelvin, 20 Kelvin, something like that, order of magnitude, okay? Temperatures. Here, Ts equal Tcmb. Tcmb is T gamma, okay? This is 0. Differential brightness temperature is essentially 0. Here, spin temperature is different than CMB temperature, okay? We expect it to go down. Then it goes up. Actually, it even gets, No, I should follow my curve. Sorry. Here, this goes down, then this goes above CMB, and then ta-da! I have reionization, I have no more signal. Sorry, my curve is really ugly. Something like that. This should be my differential brightness temperature, okay? I don't know if you have this delta TB in millikelvin. Okay, here you expect in, let's say, standard model cosmology, because at the end of the day, this is standard model cosmology, the lowest point here, okay? Just the gas temperature in standard model cosmology. Nothing special, no a priori astrophysics here. It's just the moment where it goes up where astrophysics enters. So yeah, at the end of the day, yes, it can go lower if the stars don't hit sufficiently fast, okay? But we have an idea of what is the lower point here. And this should be around 150 millikelvin. Okay? You might have heard of claims of the EDGE experiment, which have seen something much lower here. Okay? In order to explain this, you would need something that allows you to cool the gas. Okay? I'm going to discuss dark matter injection of energy. Definitely not cooling the gas, but heating the gas. Okay? So I'm not going to be able to say much. Okay, because I'm not even in agreement with, as soon as I put dark matter, I cannot even be in agreement with this picture, okay? Good. So, this is very beautiful. This is, the overall signal is like my beautiful black body spectrum in the CMB, okay? But we all know that what is very interesting about CMB is this. This is very rich, okay? Actually, hey, there is no reason you have exactly the same story in the case of 21 centimeter cosmology, but the point is that it's even nicer because CMB, okay, it's true, you have some, I erased it, visibility function, some spread. Okay, but 21 centimeter cosmology, it doesn't happen at a given redshift, okay? It happens at all redshift, okay? You have gas all along the story. So you have image of the sky, 2D, along redshift, 3D, okay? You have a whole survey volume, okay, of information. So you have essentially this, okay, image of the sky, but at different redshift, okay? So you have many images of the sky, you have a lot of information if you get to the signal, okay? What should it look like? So, careful, this is as a function of redshift, okay? This is a function of scale. But as I told you, the power of this is that I can actually fix the scale and still have information on redshift, okay? So let's say I fix the scale at a scale that we expect to be relatively free from foreground, say 0.1 megaparsec minus 1. And what do I expect here is to have some feature. So let me go to delta TB over, this is the complicated thing, delta of delta TB, okay, over delta TB squared, okay? Perturbation in the differential brightness temperature. Actually, when the gas is getting coupled, the spin temperature is getting coupled to the gas temperature, we expect a peak in this, depending on the scale, we expect a peak into the typical variance of fluctuations in the differential brightness temperature due to this Lyman alpha stuff. Okay? We actually also expect a peak here when we begin to have the gas that becomes to be heated. Okay, you have more heating there, less heating there, blah, blah, blah. You are going to potentially have a peak in the correlation function around here. Okay, and then you have ionized fluctuation. So, I mean, essentially what I'm saying is that you are going to have the perturbation in here that are going to in spin temperature that are going to be important or not, or ionized fraction that are going to be important or not, and give another peak here. So, okay, this is very ugly, but this is hand-wavingly what I expect to see at some scales, okay? And this is extremely rich again. Problem is, this depends on star, depends on dark matter distribution. You have uncertainties, okay? It's not as clean as this beautiful CMB spectrum, but you have an enormous volume accessible, okay? So potentially, once you get this information, you can put constraint on your cosmology, certainly on your astrophysics, okay? The first goal of the telescopes that are looking for this information, okay, which is, for example, the ERA telescope in South Africa that is fully built, is to actually put constraint on epoch of reionization more than everything else for the moment, okay? And above redshift, so if I draw you what we expect as an error, forget about above redshift 15 for the moment, okay? We won't be measuring these other things. Good, good. So that was, I'm going very slowly. That was for everything I wanted to tell you about 21 centimeter cosmology. I didn't ask any question up to here. Yes. Yeah. CC, you would see it essentially as at the end of the day, there is a difference at the end of the day as a overall a difference of energy, okay, between the two photons that will correspond effectively as an absorption or an emission of 21 centimeter energy. Yeah, yeah. Okay. Good. Now we go to after reionization. What kind of probe do we have there? Okay, we are after reionization, but we still have some patches of neutral hydrogen around, okay? I need another blackboard. Because I want to keep everything, to overplot my, my effect of dark matter. So, let me go after reionization. This is a very clumsy blackboard. I'm really sorry, but it's just because I want to keep my, my plot. So, reionization should be described very much detailed, okay, through the stars that are around and that are going to essentially reionize your universe. What Planck collaboration uses, what people have used mostly into CMB analysis is to just assume tangent hyperbolic for ionized fraction. They don't describe the evolution of the temperature of the universe accordingly, okay? It's good enough, okay, to give you at least a clear definition of what you measure in terms of optical depth to reionization, okay? You can simply describe it, and it's very useful. It's actually very powerful, even when you change the history of the reionization. You have much more detailed modelization that follow the ionized fraction as well as the temperature, taking into account all photoionization and photoheating processes. So you might go at the end of the day, instead of just having at reionization something that drops like a fast tangent hyperbolic, you can have something that goes smoother, okay? But will still give you the same optical depth to reionization. This is important, okay? I give you some references if you want to go to see different models of reionizations. Okay, now after reionization, I said we still have some patches actually of neutral hydrogen around. Lyman alpha forest observation enter into this game because you can have some bright beast that is going to emit some spectrum of light, okay, that could be bright around Lyman alpha transition. These guys are quasars. They are going to have a spectrum of light intensity as a function of the wavelength. I will stay in the emitted wavelength in angstrom, and you can expect, if nothing happened in the middle, to have some kind of, from some quasars, something that, a spectrum that looks like that, where this is actually the Lyman alpha wavelength, which is of the order of hundreds of nanometers or 1,215 angstrom. So this, say, is the spectrum I expect to get from my distant quasar that emits light to me, okay? These distant quasars, say it's at high redshift, say redshift 5 or redshift 6, and say that in between I have some leftover patches of neutral hydrogen, okay? What is going to happen to my beautiful spectrum is that these things are going to scatter Lyman alpha photons, okay? But not the Lyman alpha photons that are there, okay? The Lyman photons that have been stretched. Okay, so photons from the spectrum that have been stretched in wavelength. So if I go, for example, at this first redshift, okay, I'm going to have some absorptions here into my spectrum, okay? If I go to even further redshift, I expect to even have more absorption lines, okay? And at the end of the day, I get to a forest of observation of absorption lines into my spectrum of quasars. So this is Lyman alpha forest. So Natalie, now you know what it is? Yes, okay. Good. So, again, this is very beautiful, but how do we, what do we compute here? I mean, what is the relevant information? So, the relevant information is actually, it would be beautiful if it was all the spectrum, but at the end of the day, what people have been using, I mean, they use other information, I forgot what it was exactly, which also give information on what I'm interested in. But at the end of the day, what they compute is the transmitted flux, which depend again on an optical depth, okay, of Lyman alpha, effective Lyman alpha optical depth. This, I erased my beautiful drawing that was behind, but you can expect that this is going to depend on the amount of structure you have in the middle, okay? The amount of clouds of hydrogen that completely depends on the amount of dark matter you have on your way. So this is very interestingly an information about the density along the line of sight. It will also, actually the size of this absorption line are going to depend on the temperature of the medium, okay? Obviously, if you heat the medium with dark matter, again, you have an information. It depends on the photoionization rate. It depends on peculiar velocities of clouds with respect to us. This is all something that gets into hydrodynamical simulation. This is all an art, which I have absolutely no handle on. I have never done anything into that. So all I can tell you is that people have been working a lot on this, and they provide you essentially measurement of this transmitted flux, okay? Not of the transmitted flux, but again on the flux power spectrum. So they look at variance of fluctuations into this transmitted flux. I can erase this. So essentially, they look at perturbations in the flux minus the flux averaged over all possible line of sight into simulation, for example, okay? And they compute the flux power spectrum. Which is a dimensionless quantity of a certain scale kV that I'm going to define. This is just related to the fluctuation in this Fourier space kV square. In order to make things simple, obviously, they don't use redshift to measure the redshift. They talk in terms of velocity space, okay? So this, the quantity that is used is usually dV. As a measure of the redshift at the end of the day, velocity, okay? And this velocity is the Fourier dual of this K scale that is here. Okay, so if you look at Lama alpha forest papers, you will see a power spectrum flux in terms of a K that is actually in kilometers per second minus 1, okay? But obviously, I mean, just from Hubble law, okay, you know that velocity is related to distances through the Hubble rate, okay? For the same reason, kV is going to be related to the usual scale K, which is in 1 over megaparsec, which is the dual of the distances, okay, through 1 plus Z divided by H, okay? So do not worry if you see kV in kilometer per second minus 1 is just your usual K you know, but up to factors of Hubble in the between. What does my typical one-dimensional power, one-dimensional along the line of sight, because we see things along the line of sight, not in 3 dimension. In the case of Lyman alpha forest observation, typically you expect something like that, okay? Large scale, small scales, okay? This is expected to be affected by peculiar velocities relative to us, by temperature of the medium, and by the non-cold dark matter nature, okay? Especially around here, but it can also affect the rest of the spectrum, okay? But this is everything, essentially, I wanted to tell you about Lyman alpha forest data. We typically have these quasars, these bright quasars, currently in between redshift 2 to 6, okay? And we have good measurement and simulation in typically scale kV of the order of 10 to the minus 3 to 10 to the minus 1 kilometer per second minus 1, okay? You put everything together into this equation, okay? And you realize that this corresponds to scale of the order of 0.14 to 1 H over megaparsec. So this goes back to my 3-dimensional matter power spectrum of the first day, I think, or I don't remember, when I was asked the question where you have this. No, not really. I mean, you have BAO here and this goes down, okay? And this is around here, okay? This is Lyman alpha forest data, give you information on the structure, on the amount of matter along the line of sight in this region of the spectrum, essentially at relatively small K. Okay? Yes? Yeah. Yeah. Excuse me? They are scattered all over. I mean, we have only, one quasar along, we have multiple by chance. I mean, that's, that's the idea, but yeah, it's only 1D information we have, so yeah. Good, so that was about probes, okay, roughly, without going to the detail. Again, this is all nonlinear physics and astrophysics, huh? Okay? Yeah. So, much less clean information than, again, beautiful CMB. Good. So now, okay, I go. Can I erase this? Yes? Nobody against it? Okay. Very good. So now, dark matter. There are two things I would like to discuss today. Hopefully, I will talk to you about dark matter energy injection. In the early universe, would it be around CMB or later on? Let me first try to evaluate the amount of energy per redshift per unit baryons that I can get from, I don't know if I have all the factors, so let me put order off. This quantity is expected to depend on the nature of dark matter, okay, whatever it is. If I have dark matter that can inject energy. Dark matter could also be like not interacting at all, but I go, let's say, in the image of, let's say, the WIMP, weakly interacting massive particle. We know this particle should have annihilated in the early universe, hopefully like a S-wave annihilation, so where the first term is not velocity dependent. This is one of the cases I will consider. In that case, I need two particles of dark matter to annihilate, okay, so it will depend on rho dark matter square, sigma V divided actually by the mass of dark matter. And the prefactor here is actually, I said per baryon, so I divide by the baryon number density. And okay, I have a dz here, so essentially I have a factor dt over dz. So 1 plus z times h factor here. Okay. So this would be for annihilating dark matter. The WIMP case would be sigma v is a constant, okay? The vanilla WIMP, sorry. Vanilla WIMP, S-wave annihilating WIMP. If I have a P-wave annihilating WIMP, this is depending on the velocity, okay? I should take this into account. Velocity in the early universe at the time of CMB is not the same as in the late universe when structure form and dark matter is virialized into objects, okay? For the sake of this lecture, just because it's actually interesting at late time, I would also consider the possibility that I didn't consider before to have the dark matter that could decay. Could decay with very long lifetimes, longer than the history of the universe, okay? In the latter case, I just need one dark matter people to decay, and it will decay as the decay rate of dark matter to whatever you like. If it was decaying on times smaller than the history of the universe, I should have to take this into account here, okay, with an exponential. But essentially here, I will only consider dark matter that decay long, on very long lifetime, okay? I still want my dark matter to be around. These are examples. You can, if you like primordial black hole, you could have certain number density of primordial black holes that could accrete matter around them, and this can essentially accelerate particles and inject effectively energy, okay? It will depend on your accretion rate, which is, again, something very unclear, that you really have to do simulations and so on. So yeah, I will not discuss them here. But if you are interested, people have been looking at that too. And I mean, whatever you like, okay, etc., etc. So this is just to tell you I'm going to focus on this and that, but redo the analysis, please, for whatever you like, okay? Very good. So let me go back to these two cases. And let me, for a minute, evaluate the redshift dependence for these two scenarios, assuming that my dark matter is this wave annihilating. The reason why I do that is just because it's more constrained, okay? But we can discuss anything else. So I'm interested in probes of CMB and later on redshift 20 or so. So I'm essentially going to assume for a moment that my universe is dark matter dominated, okay? So h of z goes as 1 plus d to the power 3 half and not 3. Huh? So that was the question of the first quiz. In the latter case, so this goes as 1 plus z to the power 3 half. I have another 1 plus z. This goes as 1 plus z to the cube. This goes as 1 plus z to the cube to the square. Okay? You do your math, and you get that in the case of annihilating dark matter, this goes at 1 plus z to the power 1 half times sigma v, okay? I didn't put anything into sigma v. If you have velocity dependence, you should take it to account. Huh? Velocity could also redshift. In the case of dark matter decays, I have a factor of rho less, okay? 1 plus z cube. This goes essentially as 1 plus z to the factor minus 1/5 alpha times gamma, okay? There is obviously another factor I should take into account here. Because as soon as my dark matter goes into structure, essentially I have a boost of dark matter into this structure. This is why for indirect detection searches, we look to compact objects. Huh? We look to dwarf galaxies, center of the galaxy and so on. I mean, other things too, but I mean, there could be a factor here due to structure formation only, okay, only in the case of annihilating dark matter, okay? And this should definitively be taken into account. Good news, I don't know if I say it here. I might not say it, but the very good news is that CMB is so sensitive by dark matter energy injection that actually whatever expected boost we have, okay, not in very specific scenarios, okay, but usually assuming a halo mass function that is of, let's say, usual results from simulations, and halo density of dark matter as a function of distance, let's say relatively standard Navarro-Franken-Y and so on, this boost at the level of CMB constraint is totally irrelevant for S-wave dark matter, okay? So I go back to the powerfulness of CMB, it's astrophysics independent, okay? At the level of S-wave dark matter. So, I mean, this is why this is super interesting. One last thing, I mean, I'm not yet to that, but I just wanted to mention it while I was here. One last thing I should say is that this is very nice. This is injected energy, okay? I inject energy at a certain redshift, say redshift 10 to the 5, okay? Hey, it's not the photon of the same energy that is going to be at some point set into the universe. This is not a 10 to the 5 photon that is going to essentially ionize my universe and give rise to a change of this, okay? It's going to be redshifted. It's going to go through other processes, okay? Photon-photon interaction, Compton scattering, and so on. It's going to change energy, okay? So we should really keep track of the relation between energy injected and energy that is effectively deposited into the medium. Okay? This is not exactly the same. First of all, you have different channels of deposition. You have deposition into heating. Okay, first you have whatever you have annihilating into. Okay, they say W's. It's not a W that is going to ionize. Okay, it's a photon. Okay, so you first have to go to take your particles and look at the spectrum of decays, hadronization, whatever you like, depending on what you annihilate into, and you end up with electrons, photons, positrons. The others, okay, they make a small correction to all the story, okay? These guys, they are going to put their energy into the medium once they have been redshifted or whatever other processes to few keV energies, okay? And into what? Into heating, ionization, and excitation of the medium, plus photon that you can forget about once they have, no, you should not. But at least for what I'm interested in, photons below energies of Lyman alpha transition, so 10 to the 2 electron volts are left over, okay? So you should take all this into account. And usually you put it as what is called energy deposition efficiency factor, where C are the different channel of deposition, okay? It's not one, okay? It can actually be larger than one at certain redshift. If you have photon that first had to redshift, and then at the end of the day can all put their energy at some point, but most of the time this is smaller than one, okay? Good. Very good, very good. Questions? No? Okay. Now, the OLLD is what? If I'm looking at dark matter energy injection and I would like to know what is happening to CMB, I should go to my evolution equation for the ionized fraction, okay? Plug into it the amount of energy injection in the right dimension, because this is energy. I should not have energy, but energy divided by ionization energy into my Boltzmann evolution equation of the ionization rate, put them into a hierarchy, connect hierarchy to class or CAM, and look at what is going to happen to my CMB, okay? I'm not going to do that, obviously, here. You can. There are, I mean, plug-in stuff. I mean, you install class, and there is a part that is that energy injection, and you can just use it. I don't think they treat the ionized fraction efficiency as the best they can, but it's already a good idea of what is going to happen. You can do that. There are even like C files that you can just plug, and you will see the effect of dark matter decays or dark matter annihilation into there. What is going to happen? As soon as I have dark matter decays or dark matter annihilation, I'm going to essentially inject extra free electrons into my medium. In the case of dark matter annihilation, sorry, I forgot to tell you more about this. Sorry, I forgot something. Here, redshift dependency. This goes as 1 plus d to a positive power. This goes as 1 plus d to a negative power, okay? This is very useful, very well tested by early probes, Z big, okay? This is going to be much better tested by low redshift probes. So very roughly, if you plug dark matter energy injection into your evolution equation of the ionized fraction, and you look at dark matter annihilation, S-wave annihilation, what you will get is essentially a change of your plateau here that increases with increasing annihilation cross-section, okay? If you have more free electrons, you have an optical depth that increase. If you have an optical depth that increase, you increase the size of your last scattering surface, okay? You blur your signal, and what you are effectively going to change is the height of your peaks here. This is what is happening when you inject extra free electrons in the story, especially around here. it's going to, it's really because you change the amount of electrons around recombination, and that you change the size of the visibility function that I don't have anymore. So my visibility function, J eta, as a function of eta, probability of last scattering, up here is kind of peaked around redshift 1100. What happens when you have these kind of things is that this is more, this spreads to lower redshift, okay? So you have less and less, I mean, your photons are not last scattered all at the same time. They're later time, so it's difficult to have nice correlation here. Okay, so this is for dark matter annihilation. What would my boost do? What would my boost do is change this part of the story, okay? Point is that actually, whatever the boost you take, okay, with normal assumption, okay, without making things exaggerate. Your CMB constraints, your impact on this bump is going to be negligible. For dark matter decays, there is a different redshift dependency. Actually, essentially, by changing your decay rate, what you have is something that goes like that, increasing your decay rate. Point is that for the decay rate that are tested today, the effect at the time of recombination is not absolutely fantastic to give for CMB to be a competitive probe with respect to indirect detection searches today. Just because of this redshift dependency. This is why I wanted to go to this redshift dependency. Now, I'm not going to give you, I'm not going to run class in front of you. What I want to do is an estimate of the constraint that we can, I mean, what kind of dark matter candidate we can exclude with CMB, okay? So for doing that, I'm going to erase this. You are going to have order of magnitude estimate. What is essentially the change in the ionized fraction that I can expect from dark matter? Let's be very optimistic. I have lost my key, okay. Let's be very optimistic and assume that this essentially goes as the energy injected, okay, per unit baryons that I gave you before, and to have dimension right, I divide by the ionization energy of hydrogen. Let me write this essentially as n dark matter times the rate of dark matter annihilation, that is rho dark matter times n dark matter sigma v, okay? So that I can put gamma, it's either the decay rate or the annihilation rate, okay for you? Okay, if I write this like that, this goes as 1 over NB, 1 plus Z times H, rho dark matter times annihilation or decay rate of dark matter divided by the hydrogen ionization rate. Again, I can re-express this in terms of the mass of the baryons times density of baryons, which would be the rho dark matter divided by rho B. This is easy, this is order 5, okay? 1 plus Z. I have a, yes, let me collect together the rates. Gamma dark matter, and because I have rho B here, I have mass of baryons here, which is of the order of GeV, and ionization energy, which is of order let's say, of 10 electron volts. This is GeV, okay? Very good. So, now I'm going to evaluate the ionized fraction at the time of CMB, okay? So this is going to be 1000, and this is H at the time of CMB at redshift 1000. We know it's a last scattering surface, but let's take this. This is 10 to the 14 second minus 1. H minus 1 is 10 to the 14 second. And now that I have all these numbers, 1000 here, I just have to put numbers into my gamma. You agree? And where you have to trust me is that we can expect to measure at the very least, changes in the ionized fraction of the order of 10 to the minus 3 with CMB, okay? This is for sure. It was 10 to, I mean, the plateau is at 10 to the minus 4. Say it's order of 10 to the minus 3. We would like to know what are the properties of this decay rate or annihilation rate if I want to get to change of this type, in order to know what kind of properties of dark matter I can probe. Plugging all the numbers, what you will get is actually that assuming sigma v of the order of 2.2, 10 to the minus 26 centimeter cube per second, you are going to get ionized fractions larger than 10 to the minus 3 for dark matter masses larger than actually GeV. Sorry, smaller than. It goes as 1 over m. Or, so this is WIMP. It's WIMP assumption. If I assume sigma v of the order of that, I can probe masses up below GeV, according to this rule of thumb, okay? The decay rate that you are going to get is actually 10 to the minus 3 second minus 1. 10 to the 23 gamma minus 1, okay, like this. 10 to the 23 second, gamma minus 1, or lifetime of dark matter. This is very rough order of magnitude estimate. If you do the full analysis, what you will essentially get, so Planck, you go to Planck paper, you look at the section on annihilation cross-section, and you will actually see that they can probe masses below 30 GeV for dark matter annihilating into E plus E minus, okay? For that, they have taken into account that not everything goes into ionization, that depends on the final state and blah, 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 but okay, we are 1 order of magnitude off, but it gives you the idea. For decay rates, this was an analysis done by Tracy Slater and Wu, I think. I don't remember. I mean, it's in my notes. 2017, and they essentially doing the full analysis, looking at really the effect on the anisotropy spectrum. They get to decay rate tested up to 10 to the 24 second. Okay, we are 1 order of magnitude off, but it's okay. I mean, you have the point, right? I mean, you know, you see how it works. Hey. Point is that, I mean, it's cool for S-wave annihilating dark matter because, as I said, compared to other probes of indirect detection searches that can also probe this kind of annihilation of dark matter, this is astrophysics assumption 0, okay? This is linear perturbation theory, It's, to my taste, undisputable, okay? For decaying dark matter, bad news. So I said, sorry, for 10 to the 24, 10 to the 24 second is actually for masses above GeV, okay? For masses of dark matter above GeV, they get this. Actually, for masses lower, you have actually a very good efficiency in probing, in injecting your energy, okay? Let's assume an axion-like particle that decays into 2 photons for masses between EV, so KeV and MEV. You can actually, with with CMB, you can get to lifetimes of 10 to the 26 second, okay? Which is actually the most competitive probe, I would say clean probe, around in this mass range, okay? There are also astrophysics probe that comes with the same order of magnitude that comes from LEOT and galaxy, and which is order of magnitude same, but yeah. So I said bad news because for everything above GeV, indirect detection searches, they go to 10 to the 28 or 10 to the 29 second. So I mean, their CMB is absolutely not competitive. Please give me 5 other minutes to tell you about late time probes, okay? Late time probes. I said we have Lyman alpha forest observation, which I erase obviously. So Lyman alpha forest observation, what happened is that you change the temperature of the medium, which is affecting apparently the size of the absorption feature into the quasar spectrum. This has been analyzed. What I'm sensitive to now is temperature, not ionized fraction, okay? In the same way that my ionized fraction is affected by energy injection, I expect my temperature of the medium to be affected by dark matter. Let me go to this plot, okay? Ionized period is, ionization is somewhat hidden into this plot. What I'm going to expect with dark matter heating is essentially to increase the temperature of the medium well before first stars lights on with dark matter energy injection, okay? I'm also going to change the ionized fraction, but this is an epsilon effect to evaluate the effect of dark matter. So let me go to temperature evolution. Delta T from dark matter. To have the units right, I can just look at the energy injected per unit baryons, per unit redshift. So this quantity, okay? And this time, Z and H have different values depending if I'm interested at reionization, so let's say redshift of the order of 5, or 21 centimeter cosmology, say redshift of order 15, okay? CMB, Hubble rate is also different at these times. So Hubble rate is of the order of 10 to the 17 second minus 1 at redshift 15, and to 10 to the 17 second minus 1 at redshift 5. You plug this into that, okay, and as for estimate of ionized fraction, you have an estimate of the change of temperature due to your dark matter, okay? Now you have to guess what kind of change of temperature you can get, you can be sensitive to, okay? In the case of lamina for forest observation, you have observations, so this you can essentially get from your data. In the case of 21 centimeter cosmology, we don't have, okay? So the only thing I'm going to assume is that, let's assume that we could probe delta T changes, relative changes in the temperature of order 1. I didn't emphasize that, but actually temperature relevant around redshift 15 is of the order of 10 Kelvin for 21 centimeter cosmology. For Lyman alpha forest, temperature has risen very up there, and simulations and observation tell us it should be around 10 to the 4 Kelvin, okay? This plays an important role in estimating what kind of decay rates or annihilation rates you are going to be sensitive to. If I plug my numbers, let me just say that the typical interaction rate I'm going to be sensitive to is going to be 10 to the 25 second inverse decay rate, so lifetime, and 10 to the 28 second at redshift 5 or at redshift 15. Okay? So just looking at rate of energy injection, you directly see that it's much better than CMB, okay? We went from 10 to the 23 order of magnitude to 10 to the 28 or 20 to the 25, okay? So this emphasizes again how interesting it can be for a dark matter energy injection that is really efficient at low redshift. How interesting low redshift probes, and in particular actually 21 centimeter cosmology can be. 10 to the 28 second is actually order of magnitude indirect detection searches, okay? In the larger than MeV range. If you go to lower than MeV range for dark matter decay into electron positrons, you can actually see that dark matter decays, dark matter annihilation too. But dark matter annihilation, you have the boost, okay? That you should treat well, astro uncertainties. At this level, we don't have data. Let's stick to CAB. This is a super probe of dark matter annihilation. Let me focus on dark matter decay for a second. But picture-wise, the story is the same, okay? What happened? I have my dark matter that injects energy in the medium. It hits the medium. Temperature decay increases. This means that spin temperature goes from the red line here to that line there, okay? What it does here is that you expect your, can probably even make it like that. What it does, my average 21 centimeter signal, what it does is that it's going to give rise to a less absorption, okay? And potentially hitting the universe earlier. This is still approximately the same. What happens when I have my universe that is heated well before stars? In a rather homogeneous way, actually, okay? I mean, I just have less contrast. Less contrast mean, rup, rup, rup. This is what happened to my 21 centimeter expected power spectrum of fluctuation, okay? And if I have my experiment that can probe up to here, let's say, okay, I should be able to see it, actually. Okay? So what I can tell you is that Tracy, Liu, and other collaborators, they have checked for Lyman alpha forest observations, what you can get as a constraint, and you actually get to decay rate of the order of 10 to the minus 24, 10 to the minus 25 second that are probed by Lyman alpha forest observation, so similar to our order of magnitude. And in the case of dark matter energy injection through decays, okay, we actually went through an analysis where we assume homogeneous energy injection, and we get to 10 to the 28, 10 to the 29 second. So again, order of magnitude is pretty cool if you plug the right number there, okay, order 1. But this is where you get. Obviously, this depends on the history of the stars that you have. Here, this very clean feature happen if you have no early stars, okay, but we are with James Webb Telescope seeing more and more early stars, so maybe it's not so clean, and you actually have your signal again that is that you have to get out from the signal from stars, and maybe you are less sensitive, but yet you can still gain orders of magnitude compared to CMB in the range where compared to CMB probe, and also compared to indirect detection probes. So if you want the plot, the references and stuff, you can see in the notes. Voila. Other questions? I'm too late. I killed everyone. Everybody's sleeping. Good. So if not, thank you. I don't have a quiz today. I plan to do the quiz at the end of all the lectures on the cosmology. So sorry. This is why it took a little bit more time.